Hi, my name is Lucy, and this is our Steganography project. This is,
I'm Abby.
and
I'm Isaac.
so I'll be overviewing what our project actually looks like, along with the rest of my contributions, which is mainly the GUI layout, integration of our different methods, and working on method one specifically. So taking a look at the screen right now, you can see we have our title screen. This includes our instructions for navigating our program, which I'll explain to you in a second. From there, once you understand, you can click the button to continue. Now you can see here the layout. You can click different buttons to do different things. For example, you can load your initial image, so the dog image. Let's drag that up. You can load your secret image. Let's pick 3. It doesn't matter, all of them work. And then I'll be picking embed method 1 since that's the one I worked on. Clicking embed method 1 does different behavior than the rest of the methods. For embed method 1, the technique is pretty much that there are 2 axes physically stacked on top of each other in our GUI, which I've offset over here so that you can see that the images are hidden. This means that we won't be saving or loading any kind of embedded image into our MATLAB drive. Instead, all of the logic is happening on the GUI in front of you. So you can see here by clicking embed method 1, it populates different places. And then you can also see how it does the final secrets revealed. If you click recovery method 1, it disappears the original image and you can see behind it to the secret image. Now, in a normal program, a normal game, these 2 axes would be overlapped perfectly and you wouldn't be able to tell that there's a secret image. But for the purposes of demonstration, I've showed here that there is a secret image behind. Now, if we pop on over to the code, you can see how our startup function has those axes invisible until you actually click method 1. Method 1 launches into a different workspace where you'll be working on method 1 with the different axes. This technique is pretty much just resizing a lot of axes and moving them around so that you can see different things. Beyond that, the recovery is the inverse, where you instead just move the original image off of the final. As far as our regular logic that will be used throughout the program, you can see here how we have a load normal image button that allows you to pick a PNG image from any of your files. Same thing for the load secret image. From there, we also have our save embedded image folder, which is the same thing pretty much, except it goes in the reverse direction. And then the load image is all the way down here. That will let you pick an image from your file, and we can decode that for a secret image. Thank you. I'll be passing it off to Isaac to talk about his methods.
All right, so these are my functions, starting with method 2. I did 6 functions total, two basic functions of least significant bit embedding, as well as odd even embedding. And I did 3 of each technique, 1 in each color channel, red, green, and blue. I'm going to be demonstrating my red embed for the least significant bit and the odd even. So for method 2, you see I'll be explaining my function right here. This is red embed LSB. So what we do first is we copy the image to a variable, and then we extract the red channel from this variable. We use a MATLAB function called bitset to apply this information to the least significant bit, and we copy that into the actual image. From there, our recovery includes creating a variable to store this information, and then using a built-in function called bitget, which extracts the information from the least significant bit, and then converting it into a binary image. Now comes the odd even function. This is the red odd even function. As you could see, we start by making a copy of the original image and then extracting the red channel. We have these variables black pixel and white pixel, which act as a logical mask to determine if the bit in hidden image is a 1 or a 0. Keep odd and keep even just reads to make sure that everything is working. For make odd and make even, it determines if the bit in green channel does not match the bit in the hidden image, it'll change the bit of the green channel to match the hidden image. So if the hidden image pixel is odd, it will make this odd. And then you see that done here with the -1 and the -1, with the make odd and the make even. And then that's copied into the actual image. And it is recovered by making a variable. We use the mod operator to check if the bit is odd or even. and then it reconstructs that image. You'll see a demonstration of that shortly. I did this with the green and blue channels as well. As you can see, this is the green embed least significant bit and the recovery as well as the blue embed least significant bit. The same applies for the green odd even and the blue odd even. To show how these variables and functions are actually used, I'll use example methods 2 and 3, which contain the red least significant bit function and the red odd even function. So what we do is create a variable of the hidden image, and then we use a function called grayscale to binary, which I made, which basically converts this grayscale image to black and white. Then we use our function and flip the image, and then that is displayed and resized with these functions. With the recovery, we use our recovery function and flip the image as well, and then display it and resize it. I will do a demonstration of this right now. So the functions I made were method 2, 3, 5, 6, 7, 8, which contained the red, green, and blue least significant bit methods and the red, green, blue odd even methods. So you want to pick your normal image, and then you want to pick your secret image, embed. You could save it right here. Call it whatever you'd like. Load it back up, and then recover it. And you will see that it is the exact same. Now, if we do this again with the odd even function this time, we'll go through the same exact process. Embed, save. And extract the image again. And it will be the exact same. So you see that the odd, even, and the least significant bit functions work. Now I will be passing it off to Abby to show you her function. Thank you.
So I worked on method 4, and how this works is basically it identifies a secret channel is what I called it, but it's a location within the RGB array for the base image that was chosen by the user, which isn't the dog image in this case. And then we established 10 different variables that for each different RGB array for all of the potential hidden images that were provided for us. After that, we compare the image that was chosen to be the secret image by the user to each of these variables, and when it matches, we can define secret number with a value that corresponds to each different hidden image. After that, we add the secret number to the value of the RGB array for the dog image at the secret location, and that's basically how it's embedded. And for the recovery, it's just the reverse. We define all these variables again, and then compare the value of the RGB array of the embedded image at the secret location to the values of what it would be if the secret number were added. And then we can say that the recovered image is equal to the corresponding secret image. And then I can demonstrate that real quick. Image. Save. And then there we go.
All right, and that's our project. Thank you for listening to us and looking at our project. We hope you enjoyed. Some of our challenges that we've discovered when working with MATLAB App Designer is integration across multiple computers and multiple programmers can be difficult, but through working through it together, we were able to do so and develop a good understanding of steganography and especially how MATLAB App Designer works to create a user-friendly GUI. Thank you. Have a great day. Bye.
Thank you.
Thank you.